Okay, we're gonna just look at using Young's double slit equation here. Come on now. We're not gonna derive the actual equation. We're just gonna look at using it, okay? So we'll call it that. All right, so the first thing you have to understand is what exactly we're talking about when we say Young's double slit experiment. What Young did basically was a 2-point interference experiment, but with light. Okay, so if you remember, a 2-point interference um, experiment has two wave sources. You know, say in something like a ripple tank, and the waves are coming out right from the sources, traveling like this. And of course, what they're going to start doing is overlapping one another and causing these interference patterns, right, which we study. This you can see in something like a ripple tank, no problem from above, right? You can see where the nodes and antinodes are. Visible lines will appear. With light, however, you can't see it from the side. You can only see it either if you're looking directly at the light, and when you're talking about sunlight or laser light, that's definitely a bad idea, or you can see where it reflects off something. So in the case of Young's double slit, if we flip over and now say instead of this being in water, it's actually light waves, what we would observe is we would observe lines on a wall or a screen that were alternately light and dark, okay, and they're going to correspond with the central maximum that we had in 2-point interference, and the light points will be where the antinodes are, where we have constructive interference. Okay, so constructive interference, destructive interference, constructive, and so on. Okay, where the light waves are in phase or out of phase. Okay, so here's a little better picture of it that I found, and essentially what we're talking about here is, you know, if we're looking at say the central maximum here, and then we move up and we look at the first dark fringe, well, what we know is the path of light from slit 1 versus the path of light from slit 2 are out of phase by exactly half a wavelength. Okay, and if we move up to the next bright spot, we know that they're now in phase again, and therefore their path length difference would be exactly 1 wavelength. Okay, 1.5, 2, and so on. And it also turns out if you take a ruler and you measure on the wall, okay, the distances between these, you will find that the distances between adjacent dark spots is always the same. Okay? All right? So when we do this formula, it's going to just basically be based on the distance between either adjacent dark spots or adjacent light spots. That distance between those things is the same, always. Okay? And it's called delta x. So you might get a problem that says something like the distance between the first and the fourth dark spot is such and such. Okay, what you'd have to do then is, if you know that that's 4 spots, figure out what the difference is between just adjacent ones, right? So if that happens to be 4 centimeters and it's the distance between 4 spots, you know each distance is 1 centimeter. Okay, so that's basically where that that concept comes from. Okay. Now, we don't use the exact same nomenclature that this person is using here. So I'm just going to kind of redraw what we actually use for ourselves here. So let's just set this up here. All right. So you're going to have, oops, straight line here. The heck? There we go. Okay. Okay, so there's going to be your 2 openings, all right? You're also going to have center line here, okay? And then you're going to have like a wall at the other end where you're going to project your stuff to. Still struggle sometimes with exactly how to work this thing. Okay, and over here, this will be your screen. So I'm just going to label a couple of things here. So here's your slits. The distance between slits is important, okay? And we call that D. Okay, so slit width, if you want, is D. And the slits are always very, very close together, okay? Then if I go to the wall, what I'll find is I'll find a bright spot in the center, like so, and a dark spot, and a bright spot, a dark spot, and so on. So that's what this is representing, bright and dark spots. And the width of the bright spots and the width of the dark spots should be the same. Okay, right in the middle you'll have your central maximum, and then you'll have your antinodes, traveling out. So these are light spots. These are central, light, light, and then these guys are, of course, your dark spots. Dark, dark, and dark, and so on. Okay, so that's the pattern you would see, lights coming in here. We use a laser to do this. Young used a source of coherent light. I think he actually used sunlight, and he started with a single slit onto a double slit, probably through a filter, just to make sure the wavelengths were the same. Okay, then we know that if you were to have a path from slit 1, I'll make a light this color, okay, to the first dark spot, slit 2 to the first dark spot, we know that the difference between these is exactly half a wavelength, okay? Why do we know that? Because they are interfering with one another, so they're out of phase by half a wavelength. Okay, so we'll label what we're talking about here. This is the path from slit 1, dark spot 1, and this is the path from slit 2, okay? We know that the path length difference is 1/2 lambda. We know here it's 1 full lambda, here it's 1.5 lambda, here it's 2 lambdas, 2.5, and so on up. All right. We also know that the difference between the slits, or the distance, I should say, between the slits and the screen makes a difference. If I move the screen back, what I'll see is I'll see a widening out of my diffraction pattern. Okay, if I push the screen in, this compresses and gets tighter. So we call the distance between here L. Okay, and the only other thing we really need to know is how much distance there is between these two spots, because that matters as well. So we call that X, or actually it's more often called delta X. Okay, so that's the distance between adjacent dark or bright fringes. So Young's double slit experiment comes out to look like this. Basically, it's lambda, the wavelength of the input light, should be equal to delta X, the distance between the widths, times the slit width, divided by L, the length between the slits and the wall. So that's what this means, okay? Sometimes you have to figure out what delta X is because you'll be given something like, the distance between 10 slits is such and such. You have to figure out what the distance between single slits is, between single fringes, we call these, bright, light, and dark fringes. You have to find the distance between the fringes, but there's kind of where we're at with that. So let's do a sample problem and go from there. Okay, so here's a problem of the type you might see. Just grabbing something from a worksheet here. So you are measuring a setup. So a Young's double slit is performed. Where screen is 3 meters from a double slit. Okay. The slits are 0.15 millimeters apart. So So 15/100ths apart. And the distance between the first and eighth dark fringes is 8 centimeters. Okay. Find the wavelength of the incident light. Okay, so in a word problem, it can be very confusing as to what the heck they're talking about. So it's probably in your best interest to just quickly draw this setup, which we'll do. You don't have to do it every single time, but when you first start these kinds of problems, it's really not a bad idea to just do it, okay? Okay, so then we have our whole fringe pattern over here. Right, 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 etc. And we know from the first dark to the 8th dark that difference is 8 centimeters. So what we must know then is that delta x, the difference between this one and this one, should be equal to 1 centimeter. Okay? Make sense? Okay, we said the length here between the slits in the screen was 3 meters. We said that these are 0.15 millimeters apart. So we've got to do some converting there. So everything has to be in terms of units that agree with each other. So in this case, we'll change everything into meters. So we know that 1 meter is equal to 1,000 millimeters. So we get 0.15 times 10 to the negative 3 meters here. Okay, and we get 1 centimeter is 1/100th of a meter. So 1 times 10 to the negative 2 meters over here. Okay, so no rearrangement of our Young's double slit experiment necessary here. We said lambda is delta x d over L. In this case, our delta x, well, that's 1 centimeter, or 1 times 10 to the negative 2 meters. D is our slit width. That's 0.15 times 10 to the negative 3 meters. And the length is 3 meters. So let's sort out the wavelength. So by my math, we should get 5 times 10 to the negative 7 meters. Okay? Or if you want, about 500 nanometers. Okay? 500 nanometers. You can do that conversion if you want. And that is how to use Young's double slit equation. You might be asked different parts of it, but that is, an algebra problem. Rearrange this to solve for what you don't know. The end. Honestly,